by the end of today, if you read this, you will understand what quantum computing is, discover the possibilities of quantum computing, learn what qubits are, and manipulate a qubit using Qiskit on your own computer. Yeah, a lot of it we got from our prior experiences in QC, either reading the Qiskit textbook or taking whatever course we found online, watching whatever YouTube video. So a lot of it is just rehashed in this format here. You can always go online and find something else, but this is how we're going to introduce the material. Alright, so we're going to go to our computers first, and we're going to set up the environment. I don't know how many people created an account beforehand, but we'll take like 5 minutes to do so right now.
So, who here created an account before? Oh, perfect. Okay, didn't. That's completely okay. But essentially, we're going to go to the IBM Quantum Experience website. I have it pulled up right here, but essentially, if you just type IBM Quantum Experience, it's the first link that shows up. When you log in, you're not going to see this. You're going to be greeted to this webpage. If you click on the little G.
Or sign in, however you want to sign in.
Sign in, and then we're going to go ahead and click Launch Lab. And it's going to start up the server. If you use Jupyter Notebooks, this works in a very similar way. It's entirely web-based, none of the computations on your computer. So you can pretty much use any device for this, an iPad or once you log in, you're going to see a screen that looks like this. All you're going to click is this little Python 3 button over here. And once you click that, you'll be greeted with this web page. This is what you're going to use to program. Make sure that this tab over here that says code is set to code. Sometimes it defaults to Markdown or raw. So when you type something in, it doesn't know that it's code and it just keeps going on and nothing happens. When we write programs, we'll type something into a cell, such as this. You don't have to type this right now, don't worry about it. And then once we're done with a specific cell, you can hit Shift and Enter on your keyboard to go to a following cell.
So just some disclaimers almost about using the IBM Quantum Experience. There are many ways to program on quantum computers, and Qiskit is strictly from IBM. So using their platform is really only helpful if you're learning Qiskit only. It will give you a lot of experience for if you want to use another programming language on another platform, but traditionally, again, it's only useful for Qiskit on IBM Quantum Experience. Don't know if that's changed, but if you use other platforms, you can import Q#, which is Microsoft's language. I'm sure there's way. If you use Google's, probably Colab, something like that, you can get access to Circ, which is their quantum programming language. I mean, the list goes on and on. You can do Rocket with Amazon. There's so many different ways. We're starting with IBM just for easy programming, and it's definitely more intuitive, we think, and a good way to start out. So, yeah, if anyone has questions to how Jupyter Notebooks works or anything related to that, let us know throughout. So that was the quick and easy way to set up your account, start a new notebook for when you program later on. But we won't need our computers for these next 2 slides. We'll just very quickly go over classical versus quantum computing. A lot of this was taken from the first chapter of the Qiskit textbook, so you can find more detail there. So we're going to talk about classical algorithms and complexity, and what makes a quantum computer different from a classical computer, and why we even care, why so many companies are investing in this new industry. Please read the scenario on the board. If you have a numerical password, 6 digits long, how many possible combinations of digits are possible for that password if you were to brute force it because you're not given any other information about what the password contains? Yeah, sorry.
24 to the power of 6.
24? Just numbers.
6 factorial.
Close.
10 to the power of 6.
Bingo.
Yes.
Yeah.
It would be 10 to the power of 6 because you have the digits 0 through 9, and each one can occupy 1 space of the password. So you have 10 possibilities for the first one, times another 10, times another 10, 10 to the 6. That's a lot. That's 1 million, right? 1 million. And essentially this relates to how algorithms have a time based on growth and input size. So what this means is if you have a specific problem that only requires you to look at, say, the last digit of, say we're taking a different problem. How do we know if a number is even or odd? You look at its last digit. If it's divisible by 2, you know you have an even number. If it's divisible, it's not, then you have an odd number. So the algorithm only has to look at one thing. It looks at that last digit, and then it tells you whether or not you're even or odd. So that would be an algorithm that is constant time, because you're looking at one input and it takes you essentially 1 unit of time to give you the answer back. With that, here's another example, finding a word in a dictionary. You're checking each word one at a time. If you have no other information, it takes you one glance to say, is that the word? Yes or no? Keep going. You have linear time, which essentially it's like adding 2 numbers. Adding 2 numbers is linear time because if you have 300 plus 400, you add the digits right to left usually, and that's kind of similar to how a computer does it as well. So you'll get 700, but it'll take you 3 operations because you're adding the other zeros, and then 3 and 4. And then exponential time is something like the 10 to the 6th problem, where each digit can be a possibility of 10 different ones, but then you have to try every single combination inside that. So that scales up very quickly based on the number of digits that you have. Any questions?
A while loop would be linear time?
Yes.
Why loop?
So,
It depends on what's going on.
Depends what's going on inside the loop.
Yeah.
Yeah, so the actual like operators you use in a programming construct, they don't determine like how much time something takes. Now, if you have something like recursion, and you're continuously recursion, then yes, that's going to take more time than say like a for loop. But generally, it's like it's just based off of what you're trying to achieve, not how you attempt to achieve that.
Now, take 2 minutes, 1 minute, 30 seconds, I don't know, to read this long paragraph with a bunch of numbers, but take the time to really digest what's going on in this case, how we're going to relate the constant time, linear time, exponential time to real time, or using the units of time that we're used to. Okay, so essentially what this is saying is that as you scale up the number of digits in your PIN number, it's going to take exponentially longer. You can see that by the time we get to 20 digits, 120 times the age of the universe is a lot longer than any of us really have to sit around and crack passwords. So that is why some types of problems can be solved more easily by a quantum computer. I'm not saying that in particular this problem is, but there are certain kinds of problems that have this exponential time, a quadratic time, a non-constant or like linear time that a quantum algorithm will be able to solve faster than a classical algorithm. For instance, you can do some types of climate modeling. So climate modeling has so many different variables in it that if you were to try to simulate it on a regular computer, that would take even the best supercomputers, as it says here, just so much longer. Optimizing your financial stocks can be made faster, more efficient with a quantum computer. I mean, there's a lot of different possibilities, but again, only for certain problems. It's not going to solve everything, and I can't really distinguish between the types of problems right now. I can say that optimization problems are good ones for quantum computers, but beyond that, off the top of my head, I couldn't really tell you whether one problem is better for classical or quantum, but I guess generally what you should know is that it's not for every problem.
Yeah, so I have 2 interesting facts to add. Yeah, one, if you look in the history of like how quantum computers came, so the person who got the idea, I think it was Richard Feynman. But
For quantum communication,
yeah, but the idea he was thinking about doing like a quantum computer to solve quantum problems, because quantum problems take so much time on classical computers because they're so complicated. So I was like, I'm going to use that in this quantum and make a quantum computer to solve them. So I found this interesting. Just we're doing a quantum computer to understand quantum. And forgot my second part.
I was going to say in a very similar vein, battery technology is something that people are trying to use quantum computers for. The biggest thing that's stopping batteries from becoming more dense, more portable, and safer are being able to truly understand those intermolecular bonds between your different ions and such. And so a lot of investments going into using quantum computers to solve that issue. Since the only way we can make better batteries, essentially at least given our current situation, is through better, faster computational methods.
Yeah, I remember my second part. So basically, what we're expecting, like scientists expect now, quantum computers wouldn't be more efficient for something simple like sending emails or something. But for large problem like this, it could like largely beat classical computers.
So that's some of the motivation there. All right.
Sure. So now we're going to introduce the idea of a qubit. How many of you have heard of bits? Great, perfect. So bits when you look at a computer, is just either a 1 or a 0. It's a transistor you could think of. And so quantum bits are very similar in that they can be 1 and 0, just like our normal computers, except we can also make a quantum bit be anywhere between a 1 and a 0. There are many, in the way that transistors represent our classical 1 and 0 bits on the computers we have today, quantum computers represent their quantum bits in many different ways, because currently we're in a race to figure out what's the most efficient way to represent a quantum bit. Some of the current technologies include trapped ions, photons, and superconducting circuits. If you were here last week with atom computing, they're using neutral atoms as another approach. This topic is a big topic on its own, so something we can explore later. But yeah, one of the ways we can visualize, the same way we visualize a normal bit as a 1 and 0, we can visualize a quantum bit through something called the Bloch sphere, which is this thing over here. Don't be intimidated by the different symbols and stuff. All that really matters is that you have a 0 on the top and a 1 on the bottom. And there's an arrow that comes from the origin of the 3 axes that point either to a 1 or a 0. So over here, you can see that the blue arrow points to the 0. That represents the quantum bit at the 0 state. If we were to move that arrow all the way down, it'd point to the 1 state. However, we can put it anywhere in between. So my question to you is, we have this little symbol in green called psi. What do you think psi is?
A probability.
Yeah, probability. It's the probability that this quantum bit will either pick a 0 or a 1.
Maybe not pick, but yeah.
Oh, yeah. So, can anyone guess what it's, I suppose, more likely to pick in this photo?
0.
And why would that be?
Because it's closer.
Yeah, it's closer to that.
So
That's
because,
exactly it.
because it's closer, it means it has higher probability. Like if we see like the superposition equation and do the calculation to find the probability, like, this is a nice visualization.
So this mentioned the word superposition. What that means is a quantum bit can both be a 0 and a 1, but more than just being both a 0 and a 1, it can have probabilities associated with 0 and 1. So we can say that this quantum bit has an 80% chance of being a 0 versus a 20% chance of being 1 based off of where it's located. It won't decide whether it's 0, 1, or a 1 until we tell it to decide. When we tell it to decide, that's the big crux with quantum computing. Because then, as we'll see later, it may pick 0 or 1 based off of where it's positioned. It isn't finite.
And we're not like trying to personify this quantum state. It's not really deciding. It's not like live or anything. But yes, I just wanted to mention that part because that's where measurement comes in. Also, losing my train of thought. Oh yeah, just the whole probabilistic nature of quantum computing comes from quantum mechanics. So that's where your physics is going to come in. We basically are allowed to exploit the laws of quantum physics and apply them to computation and computer science in a way that this is possible, but also in a way that it's not deterministic, it's probabilistic. So you'll have probabilities once you actually run your algorithms, you get answers back out in probabilities of where the states are. If that makes sense.
And at this point, does anyone have any questions, comments, ideas? Yeah, go for it.
So you're saying you're not in control of its superposition.
So we are in control, and that's what we'll get to in the programming exercise, where we do this sort of thing.
Do the 1 and 0 correspond to like the spin or like quantum number of a qubit or something?
On a physical level,
Yeah.
yes, it can, depending on the system, of course. But I think last week, Mickey said that the atoms that they use have certain, like, I forget what it was like 10 something, I think it was 10 spin, I don't know. So some
10
programming
states.
10 states.
Yeah, so they're codifying this 0 and 1 in 2 out of 10 of the states. They're discarding all the other ones, they don't really care about them. But essentially, yes, spin up and spin down are analogs of the 0 and 1 state, depending on what system you use. So superconducting circuits, they just work on like microwave pulses and stuff like that. So not sure where the spin comes in there, but it depends. Again, it depends on the kind of system, but it can be, yes, related to spin.
Yeah, and photonics qubits, I think, determine in the state of the magnetic dipole of the photon. So, yeah, it depends on the property of the qubit system, but in general, we need something to determine, like two opposite things to determine a 0 and 1.
What I like to stress is that when it comes to the computing side for this, don't worry if you don't completely understand why a quantum bit can be in a superposition. Just for now, accept it, I suppose, and we'll dive later into that as we go. Yeah. So I think we mentioned this before. Why is it special? It's special because you can't do this with a traditional computer. With a traditional computer, you have to pick a 0 or 1. And as I mentioned earlier, it'll stay in this superposition. It'll stay in this probability of being 0 or 1 until we force it to pick. So an example that I have here that I think everyone had earlier was that let's say that I made my qubit so that it has a 50% chance of being a 0 and a 50% chance of being a 1. Where could this arrow on the block sphere back here point? Okay, go for it.
Just like to either side.
Yeah, perfect. Point to either side, and that's just because geometrically you can see it as, oh, it's halfway in between 0 and 1. That was perfect. And so that's what we have right here. So this is an example of a qubit that has a 50% probability of being 0 and a 50% probability of being 1. We're going to do this to a quantum bit now using something called a Hadamard gate. So we can think of gates as operations we apply to a quantum bit to move the arrow to some direction. So there are many gates we can apply. This Hadamard gate takes a quantum bit that is either 0 or 1 and moves it to the parallel to the x-axis. And so that's what we're going to do right now. So yeah, let's program this. So if everyone has their Jupyter notebooks from earlier, there's a chance that by the time you're opening this again, it might say like it's timed out. If it's timed out, just hit restart and it'll open up again. Is everyone in the UQA Discord? If you are, I put out a little set of import statements that you can copy and paste
In quantum programming, like in this channel.
in that channel. I'm going to go ahead and cheat and just copy them for this other document I have. And if you have a question or raise a hand, you can come over and help you out. You'll notice that when I copied and pasted it into the cell, I have this little yellow line to the left. That means that this hasn't been executed yet. So in order to run this, I can either hit this button, or more preferably hit Shift and Enter on on my keyboard, and it runs that block. The reason you're not seeing anything over here is if I were to say something like print hello world. hit shift and enter, it would press color.
Well, you can also tell because if that number in the box is an asterisk, it's still working. And if it's a number, then it's run because that's the number of times it's run something. I think people are familiar with computer.
Okay. These are the set of import statements. These first two are just statistical ones from Python. The ones that really matter are these ones over here. We're not going to go into, I suppose, what these import statements are. The only important one to mention is this import from Qiskit, rather. It's implied that you import this library called Qiskit, the programming language we're using to program on a quantum computer. If you could give me a thumbs up for if you have your import statements in, fantastic.
So also, I wanted to mention, this is the IBM Quantum Lab, so they've prepared your environment for you so that you don't have to import Qiskit because they assume you're going to be programming in Qiskit. If you want this on your machine, your actual computer, you open up some random terminal, you open up Jupyter Notebooks, and it's not a part of the Quantum Lab. There's a way that you pip install Qiskit. It's pretty standard as to how you import other libraries, but yeah, it's different if you want to run it locally on your computer versus through the website.
And if you want help with that at the end, let me sort it out. So I've gone ahead and imported everything I need. The first thing I'm going to do is create something called my quantum circuit. So the quantum circuit essentially tells the computer how many qubits do I want to manipulate or use. In our example, we're just going to be manipulating one quantum circuit. So I'm going to make a variable called QC, very creative. I'm going to type quantum circuit. And because I only want one qubit inside my quantum circuit, I'm just going to type 1. So that's created my quantum circuit. Once you've created a quantum circuit, you told the computer how many qubits you want to use, and it indexes those qubits. So if instead over here I wrote 4, I would create 4 qubits, and the computer would label those qubits 0, 1, 2, and 3. So if I were to have just one qubit, and I wanted to apply a gate onto it, I would type quantum circuit, or since we've assigned it a variable QC, dot, and we're going to apply the gate you saw earlier that moves the arrow to the center, dot H. What this does is we're telling the quantum circuit, apply the Hadamard gate that you saw earlier, but now it needs to know what qubit to apply this gate onto. And that's going to be the only qubit in your circuit. So we're going to type 0 over here, because remember, Qiskit indexes qubits from 0. So if you have 4 qubits, it's 0, 1, 2, and 3. Make sense? Questions, comments? Yeah.
I'm a little bit off topic, but how do you code? Do you code the quantum computer with the classical computer at first to get it going, or how does it work? Seems like
The IBM just simulates it with classical computers.
So, okay, the answer is you can do both. So
Yeah.
essentially you can send your code to a simulator, which will only do accurately up to about 6 to 8 qubits, because actually there's this thing that I once saw where basically simulating quantum computers on a classical computer takes up so much RAM. It takes up so many gigabytes, terabytes of memory as you scale up the number of qubits. So by the time you get to 16 or 20 qubits, you're taking up some absurd number, 16,000 gigabytes, and no one has that really on their computer. So the simulation part is really only good up to a couple, maybe 10, I don't know what the real number is. But then through this cloud, you access IBM's quantum computers that they have. They have about 5 or 6 that you can use, and you program it so that you have a back end, and the back end, each quantum computer has a name, so you'll say, I want to go to, they're named after cities for some reason, so you say, my back end will equal IBM Melbourne, or IBM
New York.
New York, and then it'll say, okay, we're gonna run your program on that quantum computer. They're not actually in those cities; they're just they're wherever they are. It's through the cloud on the server, and it'll run your program on that computer, and then give it back to you.
But also in the structure of quantum computing, on the surface with the interaction with the user, you use a classical computer.
Yes.
Okay.
I think an important, another takeaway could be that when you program on a quantum computer, the algorithms you develop need not be strictly quantum. You can have classical elements to it. So you could, for example, iterate through a data set in NumPy or in Python and then use whatever information to do some sort of quantum computation for it to give you back information to do something else with.
We are in the NISQ era, so noisy intermediate scale quantum era, which means we need to use classical algorithms in tandem with quantum algorithms because that's just the stage that we're at right now. We don't have enough qubits on quantum computers, no matter what company you go to. I'm sure they're all working very hard internally to get it done, but from what we as people can do, and even if you're at that company, I'm sure it's not there yet. So a lot of the times you'll have, whatever algorithm you're running is going to have some classical portion to it, and then also make use of quantum, but they're working together. Then you see that a lot with UQA, which is an optimization algorithm. And yeah, there's lots of people working on getting to the next stage, and someday maybe we'll have like strictly quantum like programs that don't need this. I'm not sure. We'll see.
So the next step is going to be let's visualize what we just done. And so this is the syntax to visualize that that bit you just wrote. So I'm going to write state equals state vector. We'll give you plenty of time to write that. If you're new to programming, I encourage you don't worry too much on the semantics of what I've written. The big takeaway from these two lines is that we're just telling the computer store in a variable what the state is, so where the arrow is pointing, and then display where that arrow is pointing. I've intentionally not hit Shift Enter so we can do it together. So then you guys can find my typos and we can fix them together. Because this never goes according to plan. Yeah.
Sorry, what was the .h again?
Yep. So the .h is us telling the quantum computer apply the Hadamard gate on the 0th qubit. So in other words, make the qubit go from 0 up here to an arrow over here.
Okay.
So actually, it might be really good to see where the arrow is pointing upwards first, and then see that one.
Yes.
You can just copy and paste it.
So I'm just going to copy and paste these before applying the operation so we can compare and contrast.
You could also show the circuit using the circuit similar to the
Yeah,
flow
was it
circuit
that
gain.
I don't have, it's just Qiskit. But yeah, I'm going to go ahead and hit Shift Enter and hope that nothing bad happens. Beautiful. So this top image represents what the quantum bit was before we did anything to it, and then after applying this H gate over here, the quantum bit has now moved its vector from 0 to between 0 and 1. Just a quick question: if I were, when I initialize my qubit, what does it default to?
0.
0. Yeah. So whenever you initialize a circuit, it will always start at 0. But yeah. Is everyone good to the upset?
What does it mean if it starts at 0?
Well, great question. What that means is that your quantum bit is a 0 in the beginning, the same way like your classical bit can be either 0 or 1. Like it represents 0. With our computers today, we have billions of these bits, and particular combinations of them correspond to, let's say, a cursor on your computer or a color. So in a similar way, at a very fundamental level, we're just quite literally just making a bit change its value. And if you pair a bunch of these qubits together, you can make interesting things. At least that's the goal. Everyone good? Thumbs up, thumbs down. Perfect. So this is what we had before. Now what we're going to do is we're going to go ahead and tell the computer to pick either 0 or 1. We're tired of it being on the fence. So very simple syntax. We're going to do QC quantumcomputer.measure all. If you wanted to just measure, let's say you had like 5 qubits and you just wanted to measure one of those qubits, you would just do .measure and whatever qubit you want to measure within the parentheses. But since I'm going to go ahead and just use the all syntax. Once we've asked it to measure, we want to display what it's done in a very meaningful way. So we've told the computer, hey, we want you to pick between a 0 or 1. But we haven't told the computer, oh, what machine do you want to do this on? How many times do you want to do this? Or have any idea of any usefulness for whether it's pick 0 or 1 over time. So the next thing we're going to do is we're going to tell it, pick either 0 or 1 using the computer of our choice. To do that, I'm going to make a variable called backend, which represents just the backend, just the computer we want to use. And we're going to use this function provided by IBM called AER.getBackend. And the argument we put inside these parentheses is the machine we want to do the computation on. If I had a real quantum computer, as Jade mentioned earlier, I would type IBM _ like New York.
And we can do that right now, but the only problem is a lot of people use it, so there's a queue time. There's like a wait time of, it can get very long. So essentially, if people are trying to do this from all over the world, their quantum programs are going to get placed in line to use the computer. And on average, that can take anywhere from like 6 minutes to a couple hours. So
I could try to keep it running until the end.
We could try that.
Yeah, see if we get lucky. If it can, we get lucky.
We did, yeah. In this situation, we're going to use something called the chasm simulator. I definitely didn't know that it was pronounced chasm until someone told me. But that's the simulator we're going to use. The computer that's going to do the computation we want. Now that we've told the computer, I want you to measure a quantum bit using this computer, we need to give this computer our task. That's what I'm going to declare a variable called job. And in job, I'm going to tell it to execute my quantum circuit. So you can imagine that over here, I created a new quantum circuit, but I could create maybe a second quantum circuit called QC1 with 6 qubits or 8 qubits or so on. So this argument over here just tells us that we want to execute a job on this quantum circuit using the backend computer we defined up here. And then we're going to tell the computer to do 1,000 shots. Any guesses on what a shot could be? Go for it, yeah.
Since it's a probability, the amount of times you run the program. Yeah.
You can just speak up a little bit.
Since it's a probability, the amount of times you run the program, the values are average.
Exactly. Why would we want to run this circuit 1,000 times? Like, what's the motivation? Yeah, go ahead.
Because you could get different responses every time you run the program.
Exactly. That's perfect. Because it's in this superposition, we could get different responses, and so we do it a certain number of times. I don't know why I picked 1,000. Convention had it, but yeah, entirely arbitrary. Now that we've done the job, we want to store the result of this computation in a variable. So we'll do result equals job dot result. We've stored our result for. Let me make this a little. There we go. Can everyone see? Okay, it might be too long on the screen. Okay. We've stored our job. The next thing we're going to do is make another variable that stores all the different answers it received. The zeros and ones from doing this 1,000 times. I'm going to call that counts. I'm going to tell it result.get counts. And now that I've stored now that I've stored whether it's a 1 or a 0 in those 1,000 times, I'm going to plot this in a histogram. So just very simply plot histogram counts. Notice that, as you may have mentioned earlier, a lot of the the functions we're using are actually classical. So this plot histogram command is in the NumPy library. So we're using a lot of our classical functions and methods to do quantum computations. Is everyone good till this point? Thumbs up, thumbs down. Okay. I'm going to go ahead and hit enter. And when I do that, I get this probability. As you mentioned earlier, if this was a perfect world, we should see a 50-50 probability. 500 times it would pick 0, 500 times it would pick 1. But every time I run this, we get slightly different values for whether it picks 0 or 1. Why might that be the case?
Noise.
Noise, yeah, exactly. So go ahead.
I got 0.5.
No, you got it perfect. If you keep hitting enter, does it change?
Yeah.
Okay, great. Then we're good. Yeah, this is a slideshow. That's great. Yeah, you're exactly right. It's noise. These computers aren't perfect. And so even though we're running a simulation, this chasm simulator aims to try to predict what noise is like on a real quantum computer. So that way you don't have to keep sending jobs to one. You could, if you have a small algorithm of data use, you can simulate it on your own computer. And once you're ready, do the actual computation on a real one.
And the Chasm simulator is a noisy simulator, so it'll input its own simulation of noise in addition to your program. Essentially. It's not meant to be.
If you're curious, they have, Qiskit's very well documented, they have all the types of simulators that you can use. Clipper, and it tells you like how exactly they're trying to simulate that, what type of uncertainty. So yeah, this is essentially you've just programmed on a quantum computer. You've made a quantum bit, you've done some stuff on the quantum bit, you've applied a gate, and you've asked to pick either 0 or 1. Yeah. Does anyone have any questions? Cool. Oh yes.
So once again, the purpose of the Hadamard gate is just to bring it to the 0 state.
Yep. The purpose of the Hadamard gate is to move the vector 90 degrees along the x-axis. So there are many types of gates that we'll get into, but let's say your quantum bit was like this, and you moved it, you applied the Hadamard gate, it wouldn't go down here, it would move 90 degrees to like over here. And so, getting into that, there are many types of gates you can use on quantum computers. This is just one example, because I think it's a cool example. But there are different things you can use. So for example, there's a gate called the PAL-D-X, or just the X gate, which essentially moves something from a 0 to a 1, just like a traditional bit does. There's PAL-D-Y, which does the same thing, but along a different axes. And in future talks, we may discuss why would you want to go from 0 to 1 on a different axes. PAL-D-Z does a rotation that way. The Hadamard gate, which we just did, goes, I didn't quite show you, but it goes to the center in quite an interesting pattern about, I think, the y-axis. And then you have phase gates, where you can move it at particular angles, like T-gates. Was anyone here, were y'all at the talk from last week from Adam Computing? What's the one question he asked everyone to ask a quantum computing startup?
What's your gate set?
What's your gate set? So my question to you is, I have all these quantum gates I can apply. Can I use all these gates on any quantum computer I'm given? No. So there are plenty of gates, and so when you actually program on a quantum computer, you have to consider the limitations of that computer. For example, if I want to get from 0 to 1, I can apply our Hadamard gate twice, because it moves from 0 to the center, and again, it goes back to 0. It goes back to 1, or I can use the X gate. But me picking the H gate or the X gate depends on whether that can physically be done on a quantum computer.
So
yeah.
when we apply a Hadamard gate, is in a quantum computer is an atom actually physically moved by a certain distance?
So from earlier, there are many ways to represent a quantum bit. So it's just dependent on the implementation used.
Alright.
So a lot of computers use how excited an ion is as what location it's at. So like the energy level of an ion could be a representation of, its energy level is halfway in between one state and another state. So it really depends on how the qubit's being physically represented.
But usually the answer is no, because the block sphere is just a geometric representation. Our arrows pointing up to 0 or down to 1, like those aren't actually like apparent in a quantum system. It's just a way to learn it and wrap your head around the concept of possibilities being on a sphere. So the block sphere is purely geometric and is really only helpful for one qubit or single qubit states, because as soon as you get into 2 qubits, it's very difficult to show like exactly how that state is, especially on one sphere. So more of like a learning tool.
Yeah. Moving forward, it's a lot easier to represent quantum computing using linear algebra. A lot of people call linear algebra the language of quantum computing. And so, if you notice from the website, in addition to these visualizations on the qubit, each gate also has a matrix associated, and you could multiply that with the matrix of a quantum bit to get a numerical solution, which represents the same thing as this. And so, to truly leverage quantum computers, it's essential to, I guess, also understand that, these gates are just matrices. And that's something we can get into later. An important thing we didn't mention is entanglement. 2 quantum bits can be entangled. What that means is that the state of one quantum bit is dependent on the state of another quantum bit. So you can have it so that if one quantum bit is at a 1, the other one will always be the opposite. Or if the other one's at a 0, the other one will always be at a 1. This is very different to classical computers, because in classical computers, your bits are independent. If I have 2 regular bits and I set 0, and I make one 0 and the other 1, if I change one of them to 1, that doesn't affect the other bit at all. And so leveraging the use of entanglement is what makes quantum computing so enticing. Yeah?
How do they become entangled?
Oh,
Cool.
great question. Do you want to?
Me?
Yeah.
Well, there is like multiple ways. Don't know the details, but I know for like iron trapped qubits, they use lasers to entangle them. What the exact physics going on to do that, I don't 100% know.
Yeah, that was a really good question.
Yeah, you're talking about on a physical level, how
How do
do
you entangle?
how do your qubits entangle?
Yes, I guess like the laser system, or like that's online.
It would be, again, it would depend on the physical system. Entanglement is like a key resource for quantum computation, so essentially,
In general, like the 2 qubits, I think, need to get entrapped with each other at some point to get entangled. And after that, doesn't matter how much they're far apart from each other, they still have some sort of connection.
I love that.
Yeah, I think that's everything.
cool. It's 9 minutes. Another thing I wanted to show was if you go back to your, dashboard, you scroll down to your IBM Quantum Compute resources. You can look at all of the computers they have available. This is what we were talking about. Washington, Ithaca, random cities.
One.
Actually, I found one that has 0 jobs.
Really?
Ithaca.
It's,
Yeah, in the beginning.
See, this one has 533 jobs. It would never run in the time that we had in this meeting, so high demand.
yeah, so you'll also notice some of them have a lock sign next to them. If you want to use the computers that have the lock sign, you need to buy an API token from IBM. But if they don't have a lock sign, you're free to use those computers. So we could try.
They're now
That's why Ithaca has a long time.
If you want to try, like.
Oh, also, one more thing. You can also do, if you want to visualize what your quantum circuit looks like, That just gives it a format.
Should-
So we applied one Hadamard. The barriers are kind of just put there. Why are there three registers?
There's also another, like in IBM, they have another system where you could build these yourself.
Right.
Oh,
The
yeah,
circuit simulator.
Yeah, there's a lot of functionality on this. You can do a lot of things. You can go to your composer. So we're in the lab right now, but you can go to the composer and basically drag and drop gates onto your circuit and then see how, and then that will just run it for you. It even programs it to the side for you so that you want to know what the corresponding code is. It's really helpful.
Think of it as a scratch for quantum computing. I guess we can quickly go over how to read this. So the way you read that is that each line represents a qubit and what you do to it. So if I have 3 qubits, I'm going to have 3 lines. The top one's going to be my 0th qubit. This is going to be my first qubit. This is my second qubit. Different programming languages actually index very differently. So some choose to label this the 0th qubit and this the second qubit. But IBM chose this to be the 0th qubit and this to be the first, this to be the 3rd qubit. And so if we, in our example, we applied a Hadamard gate on our one and only qubit, you would represent that as just a physical block with an H. And then once you apply, and you could apply a bunch of these gates together. So like, let's say I wanted to apply, as I mentioned earlier, that Pauli X gate. I can apply another gate like that. And once I'm satisfied with how many times I want to move that arrow, I can do something that reports as a measurement, which is just like a little, is that a speedometer? I
Yeah.
don't know how to draw a speedometer
Little
like that. But it's a speedometer. And then it picks either 0 or 1.
Yes.
What is it like writing and assign? What language is that? Is that like
So, so what that does is, that's a very good question. So what happens is that when you create a quantum circuit, in the back end, Qiskit assigns a quantum bit to a classical bit on your computer. Okay, this quantum bit is going to output a 0 or a 1 on this specific regular bit on your computer. And so, for example, if I made a circuit with 4 quantum bits, in its background, in the back, it automatically creates 4 regular bits to store that information. And so they call it the classical registry and the quantum registry. So QReg and CReg. Yeah.
But quantum bits can take values between 0 and 1, right? So
Yep.
how those occur?
Yep, so quantum bits can take values between 0 and 1, and it only assigns a 0 and 1 to its classical neighbor once you tell it to. So that classical bit stays at 0 until you tell its quantum neighbor, pick between a 0 and 1. Once it picks, that classical bit's assigned a 1. That's what you see on your computer.
Well, generally when we say it's between 0 and 1, it's more like it's a sort of combination of probability of 2. It's not like it's between 0 and 1. It's not like it's 0.5 or something. It's not a specific number in between.
It's
Just-
probabilities of
yeah.
0 or probabilities of 1. And we as humans, we will only ever see 0 or 1 anyway, so when we force the measurement, we have to get 0 or 1. We can't really get anything in between.
And the easiest way to show that is using linear algebra. That's the connection to why it's so important. Oh yeah?
I was just gonna say, so like with that, it's like creating a quantum registry of 4 qubits and then like classical 4 bits, and then applying Hadamard to the 0th bit, and then it's like converting the 0 bit from a quantum to a classical bit.
Yes, it's measuring the quantum bit to the classical.
Yeah, so they're mapping it sort of. Like
Exactly.
Quantum to a classical. Yeah.
That's exactly what's happening.
I want to say that this whole side panel is like a pseudocode or some sort. I haven't actually seen it before. It must be like a new edition. I think opening in Quantum Lab will actually give you code written like this, like your normal lines.
I'm trying to open it.
Open queue seconds as well.
Well, we take questions. We could try running it on a real computer, and then hopefully let it take questions.
Which computer is open to?
I think I wrote this. Ithaca.
Ithaca is, it's called, like, it has a lot.
Okay.
It tried with Intron, obviously.
You had a question, right?
Just that, do all the computers that IBM have use the same gate set?
I don't know. My guess is probably for like universality, but I actually don't know. I think if you type IBM quantum computers and you click on them, they give you their gate set. That's a good question. I'm not sure.
It does show, like, when you're looking at the quantum things, it says, like, the different processor that they're using.
Oh, wait, like it okay.
Like, that's what that symbol is in the bottom right corner. If you click on it, it says, like, the processor. That one says Falcon, but, like, the ones that you can't use, some of them are different processor types.
Interesting. Yeah.
So maybe that's it.
Another cool thing to look at when you're looking at computers that I'll mention in the last minute here is their configuration, their physical configuration. Here you can see it's a line, but sometimes it can be a bow tie or it can be some other configuration that when you're doing multi-qubit gates and operations, it affects how you do it. For instance, the 0 and the 4, they're not connected anyway. So if you wanted to induce entanglement between the two, it might not be physically possible on this specific computer because they're not connected. So when IonQ boasts that all 11 of their qubits are connected, I mean, that is pretty important because you could say, I want 1 and 3, or 1 and 9, or like 2 and 5. However, on this one, you really just can't do 1 and 4. You have to do 1 and 2, or 2 and 3, something like that. So interconnectivity is another like kind of cool thing that's a feature.
Yeah, here it says basis gates. I think this is their gates. Where is it? Basis gates.
Oh yeah.
So for something like that where it's linear, I'm assuming you can only entangle its neighbors.
Yep.
Could you get like 1 and 4 connected by entangling 1 with 2 and then 2 with 3 and then 3 with 4? Or is that not allowed?
So can you chain entanglement? I don't think so.
As far as I know, entanglement is between 2 qubits. So even if you, yeah, you can. Even if you try to, if you have 2 entangled qubits and you got the third one and try to entangle this one with one of them, the entanglement, the original one will disappear.
Once you apply a entangled gate, it's telling you, okay, this one is, for example, if you apply a gate so that one is, if you have 2 qubits, one's a 1, the other's a 0, this one's a 1, make this one a 1 as well, and then you try to entangle that qubit with another qubit, it will have to do that measurement before trying to entangle itself with another, rather than a continuous chain.
I think that's also only for maximal entanglement. So there are these things called Bell states, which are maximally entangled 2 qubit states, and I think you can have like 3 qubits entangled, but they won't be maximally entangled. They'll only be like slightly entangled. So if you want the stronger correlation that you get, it's really only between 2.
I need trademark on that.
Yeah.
But like, even I remember one of the cool stuff about entanglement is called entanglement swapping, which is if you have 2 pairs of which is like total of 4 qubits and each 2 are entangled, then you try to entangle 2 of the non-ones, the whole thing swaps, which is also cool.
That is very
Yeah, this is the different configuration. Anyway, that's kind of like a little bit of the tour of the IBM Quantum Experience platform. There's a lot of things you can do. We haven't unlocked every single thing, every single feature, but yeah, those are some cool things. Hope that you enjoyed like getting used to all the different features, and we plan to have sort of like more quantum computing specific lessons and or meetings, using different resources, not just this one.